In this video, we are recording grade 11 worksheet number 1. So what does EMF stand for? EMF stands for electric motive force, and the N is the number of turns, and this sign with a circle and a line through it is the magnetic field strength, and the T is the time. Now in the second formula, EMF is equal to negative L. So what will L be? L will be,
L is the inductor value in Henry.
and the triangle on the top will be delta, which means the change in the amps, or in most cases is going to be milliamps, and T will be the time. So remember that when we move a coil in a magnetic field, an EMF is induced into that coil, and the faster we move it, the more EMF will be generated in that coil. So this is why time is something that's there, and also the strength of the magnetic fields there, also the number of turns, also the length of the coil. Then we have something called MMF, which means the magnetic motive force, but it's also used as F with a small m. And we got a formula: Fm is equal to In. I is the current, and N is the number of turns. Okay, so our unit there will be amp turns. And then Fm is equal to H. Now H is the amp turns per meter, and we have times L, right, which is the length normally, and this will be the circumference of the coil. Then we have C is equal to 2 pi r. We know C is circumference from mathematics, but C is also equal to pi times diameter. So 2r is the diameter. So this is why the formula is C is equal to 2 pi r, or C is equal to pi d. Question 1 says, calculate the EMF induced into the coil when the magnetic field moves across the coil for 3 seconds. So let's write down the information that we have. So here, the information that we have the Webers, which is the magnetic field strength, which is 0.3 Webers, and the time is 3 seconds. We are trying to calculate the EMF. And so we will use the formula negative N times the Webers over the time. Why negative? Because the EMF induced is in the opposite direction according to Lenz's law. So let's substitute. So substituting the Webers over the time, don't forget reading the question. It says that the coil is 400 turns N. So we're going to substitute 400. This will give you an answer of negative 40 volts. Don't forget to include the negative. That is question number 1 completed. Question number 2, calculate the back EMF induced into the coil when the current changes from 700 milliamps to 100 milliamps in 400 microseconds. The self-inductance is 2 millihenries. Let's write down the given information. So first we have the change in current. Converting that into amps, we'll get 0.7 all the way to 0.1 amps. Then we have the time. The time is 400 microseconds, which will be 400 times 10 to the minus 6. And then we are given 2 millihenries. So 2 millihenries, that's probably going to be the L in the formula. So notice the formula there is EMF is equal to minus L. So L is not the length, L is the henries. So the formula is minus L delta over T. So delta is the change in the current, T is the time. This L is not actually the length, it is the henries, millihenries in this case. Let's substitute. Now millihenries is negative 2 times 10 to the minus 3. And then our change in current. And then we have to put the time. which is 400 times 10 to the minus 6. Then plugging all of that into the calculator, we should get, don't forget the negative 3 volts, and that is question number 2 completed. In the next question, question number 3, it says calculate the magnetomotive force produced by a coil of 500 turns when a current of 0.2 amps flows through the coil. So this is kind of an easy question, right? So using the formula, so substituting the values, I as 0.2 amps and N as 500. And don't forget our unit there will be current multiplied by turns. So our unit will be amp turns. And the answer is 100 amp turns. Question 4 says a circular coil has a radius of 8 millimeters and a field strength of 5,000 amp turns per meter. Calculate the magnetomotive force. So given here we have a radius, which we have to convert to meters. We have H, which is the field strength per meter, and it's given as 5,000 amp turns per meter. So look for a formula that you can use. So the magnetomotive force, which is Fm, is equal to H. That will be the field strength per meter times the length of the circumference. Don't forget that Fm is the magnetomotive force, okay, which is in amp turns. So notice that H is amp turns per meter. So this means all we're doing, we're multiplying the Fm times the meters. Okay, that's practically what we're doing. So substituting for H, which is amps turns per meter, and then we're multiplying it by meters. So notice there, we got a radius. Okay, now we need to get the length of the circumference. Do you see it? The length of the circumference. So circumference is equal to 2 pi r. Okay, so our formula will be H is equal to, Fm is equal to H times 2 pi r. Okay, does it make sense? Because length of circumference will be 2 pi r, and there's the H. So H times 2 pi r would be the formula. Plugging all that into our calculator, we should get 251.33 amp turns. In the next question, it says calculate the current that creates 251.33 amp turns and the coil has 400 turns. So they say calculate the current that creates a Fm of 251.33 amp turns. So we know that Fm, magnetomotive force, is equal to I times N, the current times the number of turns. We have to make I subject to the formula. So I is equal to Fm over N. The next step would then be to substitute the values, 251.33 over 400. Plugging it into our calculator, we should get an answer of 0.63 amps. That is question number 5 completed. Question number 6. Question number 6 mentions something called an ideal transformer. Okay, so ideal means that it's perfect, meaning it has no losses that are taken into consideration in this calculation. So the question says an ideal transformer has 80 turns with a primary current of 0.4 amps. This means that's going to be on the left hand side, and the secondary coil has 200 turns. If the secondary current, find the secondary current, calculate the power of the transformer if the secondary voltage is 55 volts. All of that is a lot of information. It would be best to draw a transformer and write the values as N1 as being the primary, N2 being the secondary. And N1 versus N2 gives us something called a transformer ratio. So with a transformer, we have a primary side, which is denoted on the left as 1s, and the secondary side, which is 2. So the primary side is also called the input, and the secondary side is called the output. Reading the question, it's clear that the transformer has 80 turns on the primary, and the secondary coil has 20 turns. So let's write N1 and N2 first. Then primary current of 0,1 amps. And a secondary current is not given. They also want us to calculate the power. So we get something called a transformation ratio, which this question doesn't say, but if it said calculate the transformation ratio, then it will be N1 over N2, which will be 80 over 20. Dividing 80 by 20, you'll get 4. This means the number of coils is 4 times greater than the coils on the secondary. This means this would be a step-down transformer. So when the coils are greater on the primary and less on the secondary, this means the voltage will step down. Okay, so the voltage is directly proportional to the turns, okay, but inversely proportional to the I's, the current. So the transformer ratio denoted by small little n, right, is 80 over 20, 4:1. So notice that this here would be a step-down transformer. So those are the type of questions they will also ask in the test. So let's go and look at the formula to calculate the current. Now the formulas can be flipped. You can have I1 over I2 equals N2 over N1. Do note it's not I1 and N1 in the numerators. Do notice that it's I2 and N1 because it's inversely proportional. Okay, so why did I write I1 on top? I wrote I1 on top because I1 is what I'm trying to find. So the thing that you're trying to calculate, make sure it's on the left and on the top. So in this case, we are trying to find the secondary current. Manipulate the formula by multiplying I1 on both sides. And this is what we would get. Okay. Or because we're dividing by I1 on the left, this means take it to the right hand side. It will be multiplied by I1. Okay. Now I1 is 0,1. N1 is 80 and N2 is 20. Mistake. I1 is not 0, okay, so do note that I1 is not 0,1, it is 0,4. I made a mistake there. Right, plugging that into your calculator, what do you get? 1,6 amps. Okay, and then we're going to calculate the power. Now the second part of the question says calculate the power if the secondary voltage is 55 volts. Okay, so notice I didn't write that on the screen. Okay, so calculate the power if a V2 is 55. Right, so notice if you're calculating the power, you can only use the secondary side information, or you can use the primary side information. But notice we do not have a V1 here. There's no V1. So that means we're going to have to use the secondary side. Now remember that with a transformer in grade 11, power in is equal to power out in an ideal transformer. So we said that the voltage is 55 on the secondary and our current which we calculated was 1,6 amps. We will then get an answer of 88. That is question 6 completed. We then go into question number 7. Reading question number 7, the primary coil has 100 turns with 220 volts at its input. So do note that it's using the word input now, which will be the primary. Now it speaks of the secondary. It provides, that means it's on the secondary side. It provides 0,4 amps with 25 turns on the secondary coil. So now they've given us 0,4 amps, which would be current, and 25 turns on the secondary coil. Right. The question should read, calculate the secondary voltage and the primary current. Right. The question should read, calculate the secondary voltage and the primary current. Okay. So primary currents will be I1, secondary voltage V2. So let's go and calculate that secondary voltage first. So do note that they are in direct proportion, okay? The turns versus voltage will be in direct proportion because we are either stepping up or stepping down the voltages. Okay, so let's find in V2. Let's make V2 subjects of the formula. Now notice that the question didn't ask for the transformation ratio, but it could, and that would be 100 over 25. It's always N1 over N2 for the transformation ratio. So 100 divided by 25 would give you 4. And so you'll have 4:1 as a transformation ratio. Right, so substituting 220 and then N2 over N1. I think I put the wrong numbers. Okay, and correcting that, N2 over N1, so it's 25 over 100, right? Multiplying that all out, how much will you get for V2? Notice that this transformer is a step down transformer because we have 100 turns as N1 and 25 turns as N2. So we're stepping down the voltage. So ask yourself the question, did the voltage step down? Do note that V1 is 220 and V2 is 55. Notice that the voltage did come down. The next question, they want us to find the primary current. So following this, you can use any one of these methods because notice that the voltages are proportional to the turns. And so those are your two formulas. So to find the transformation ratio, I can also use V1 over V2 to find the transformation ratio. Okay, so making I subject to the formula in both cases, I'm going to do both at the same time. Now let's substitute for I2. I2 we said was 0.4 amps, okay? And N2 was 25, N1 is 100. Then V2 is 55 and V1 is 220. Do note that we get the transformation ratio as 1:4, whether we use the voltages or the turns. Okay, plugging it into your calculator, we'll get 0.1 amps. Okay, and that is grade 11 worksheet number 1. I will do worksheet number 2 in another video.